So now we'll see the tutorial on the state feedback controller design. So this tutorial is divided into two parts. Today we'll become covering part one, covering first half of the overall module state feedback controller design. So 6 problems we would consider to cover the modules. So the first 2 problem deals with the different aspects of the state feedback controller design, and these notes you can take from the lecture slides from 10 to 15. Third problem will deal with the BIBO and asymptotic stability with the state feedback. So this BIBO and asymptotic stability concepts were introduced in the week 2 of stability. We will see that how they are affected or they are influenced under the effect of state feedback. Fourth, we will see the limitations of eigenvalue placement, that what eigenvalues we can place arbitrarily. The fifth problem deals with the state feedback design using 2 methods we have introduced during the theory classes. First, using the Lyapunov method, and another we will directly show with the place command. So this place command is basically equivalent to the eigenvalue assignment method we have covered during the lecture slides number 18 to 23. The last problem deals with the state feedback and the tracking problem. So in the problem 1, we have a LTI system given to us with A, B matrices where U is a single input variable, and we have 2-dimensional system. We need to find the stabilizing feedback matrix or the feedback gain vector K, and Hurwitz closed loop matrix A plus BK using the controllability Gramian Q. So this problem we have introduced in the tutorial problems because this gives a new viewpoint of designing a controller using the controllability Gramian. In the lecture slides, we had seen the eigenvalue placement by either using the Lyapunov method or the place command. So here we would design the gain vector K by using the controllability Gramian Q. So first we will introduce the method, that how you could use this method to compute the state feedback gain. So the result says that the feedback matrix K given by as minus B transpose Q inverse produces a Hurwitz closed loop matrix A plus BK, which is equivalent to this one if I substitute K from here to here, where Q is the controllability Gramian. Okay, so in the controllability week, we had seen that how to compute the controllability Gramian. So once we computed that Gramian, the B matrix is already known to us. So by using this formula, I can compute the state feedback gain. Okay, so let's see the proof of this one. So we know onto the left hand side is basically similar to what we had seen as the Lyapunov equation during the stability week. Since we need to prove or we need to show that the closed loop matrix is Hurwitz, so we will take the help of the Lyapunov equation to show this result. So if we recall the left side, it is the left side of the Lyapunov equation, AQ plus QA transpose. The controllability Gramian is computed using this method where we have this A transpose T. Okay, so A times Q plus Q times A transpose and the overall integral. So here we are using the integral from 0 to capital time T. Otherwise we could take it also from 0 to infinity. Now if we see this integrand we can express this as the derivative of this quadratic form, okay, which is being integrated from 0 to T. Now solving this definite integral, we obtain this onto the right hand side. Okay, but this only shows the stability of the plant itself, and we need to show the stability of the closed loop matrix. So if I apply the same result, so the closed loop matrix is this one, And now replacing this A matrix by this A matrix, we can write the left hand side and setting K is equal to minus B transpose Q inverse, because we want to show that for this state feedback matrix, the closed loop matrix, the closed loop state matrix is stable. So simplifying this expression onto the left hand side, we get this one, which further simplifies is 2AQ plus QA transpose minus 2BB transpose. Now this part we have already seen from the above. So if I substitute this one to here and simplify further, we obtain minus BB transpose minus e to the power minus t into a BB transpose e to the power minus TA transpose. Okay, so we need to show that for the stability, if you recall the Lyapunov stability theorem for the LTI system, Q is already a positive definite matrix. Okay, and this is the matrix of which we want to show the stability. So we need to only show that the right hand side is negative definite. Okay, basically, so we'll deal with this equation. Now we define another matrix, let's say B hat, defined as containing two block matrices B and exponential matrix times B. Okay. And note that the right hand side of the equation above may be written as minus B hat times B hat transpose, because if I simplify this expression, I will get this one, which implies that the previously obtained equation is basically the Lyapunov equation, and finally we obtain this. Now we only need to visualize whether this matrix is positive definite or not. So since the original pair A comma B is controllable, this new or closed loop state matrix with the or paired with the matrix P would also be controllable. This was one of the results. Now from the definition of the B hat, it follows that this pair would also be controllable. Because why? I can express this B hat as I n e to the power minus TA times B. Okay, now this matrix would be a non-singular matrix, definitely. So pre-multiplying with a non-singular matrix would not change much of the properties of the B. The rank would remain the same. So meaning to say, this closed loop state matrix paired with another B matrix, which is B hat, would also be controllable. Now since Q and B hat transpose are positive definite matrices, we conclude that this pair would definitely be Horwitz. Now this is easy to visualize that why this matrix would be positive definite matrix. So see this part. So B into B transpose would be positive definite, or would less, or at most, oh sorry, at least it would be positive semi definite. It cannot be negative, right? Now this part, because of the exponential matrices, it would always be positive definite. So if I add a positive semi-definite matrix to a positive definite matrix, the resultant would always be a positive definite, right? Because of this, we conclude that this matrix would always be a Hurwitz matrix. Now coming on to the problem, we want to design the controller. We have this AB matrix. So for computing the controllability Gramian, we need the exponential matrix of the A matrix. So once we compute, we get this exponential terms, and at the same time we notice that A transpose is equal to minus of A. Thus we can also write this one, that e to the power minus A transpose T would be equal to e to the power AT. Okay, now if you recall that we need to compute the controllability Gramian over some time t or to infinity. Now all these terms are the sine cosine terms. So it would be, if I integrate them from 0 to infinity, it would be infinite. Okay, but we also know that they are periodic in nature. Every term is periodic in nature, so I can compute over 0 to 2 pi and finally write the result in terms of, or by choosing t is equal to 2 pi. Okay, so computing this matrix, so we substituted all these parts. This is the exponential term, b transpose, and again the exponential term. So solving this definite integral on direct integration, we obtain the controllability Gramian as this matrix. So these are pi, right? So this would definitely be a positive definite matrix. Okay. Now calculating the stabilizing feedback matrix as k is equal to minus b transpose q inverse, we finally obtain this state feedback gain vector. Now next you can verify the closed loop state matrix, whether it is Hurwitz or not. So by computing the eigenvalue of this matrix, you would see that this matrix is Hurwitz. So here we have presented another way of computing the state feedback matrix by using the controllability Gramian. In the problem 2, we discuss the discrete time controller design, where we are given the AB matrices of a discrete time system and also the C matrix. The first part A deals with finding the state feedback gain so that the resulting system or the closed loop system has all the eigenvalues at x is equal to 0. Now do not confuse here. So x is the state basically. So all the eigenvalues should be located as 0. So it should not be x is equal to 0. Note that you should not confuse here that we are not in the continuous time domain, because if we are in the continuous time domain and locating all the eigenvalues at 0 would result into an unstable closed loop system. But in the discrete time, placing the eigenvalues are 0, meaning that all the eigenvalues are inside the unit circle. Okay, so we need to design the state feedback where we are placing all the eigenvalues at the origin. The next part, we want to show that for any initial state, the 0 input response of the feedback system becomes identically 0 for t greater than equal to 3. So this is a important part, that here once we go into the proof of this part, it is obvious that for any initial state we can have the response of the feedback system identity equal to 0, right? So we'll come on to this part once we see the solution. Now the B part, we are introducing another feedback which is given by u is equal to PR minus kx, where P is the feed forward gain and K is the same state feedback gain what we have computed in the part A. Now here we want to find again P so that the output will track any step reference input. And the next part says that we want to show that y of t is equal to r of t for all t greater than equal to 3. So first we'll take up the first part for placing the eigenvalues at 0. Note that here you can compute the eigenvalues of the A matrix since it is an upper triangular matrix. So all the eigenvalues are located at 1. And we know that it is an unstable system because it is a discrete time system. Okay. Now first of all we need to check the controllability of the pair A comma B, which you can do by computing the controllability matrix and then checking the rank of it. So here we will carry out the design using the eigenvalue assignment. This delta z is the characteristic polynomial of the plant, and this characteristic polynomial is the desired characteristic polynomial. So because if you compute the roots of this characteristic polynomial, it would be multiple roots located at 0. So first we compute the k bar, which is computed by the differences of the coefficients of the z having same powers. Since all these coefficients are 0, so these k bar can be formed directly with the coefficients of the characteristic polynomial of the plant. Now the gain k can be computed by using this formula, where k bar we have assigned by having the information of the characteristic polynomial of the plant and the feedback loop, and then the controllability matrix multiplied by its inverse. So using this equation, we can compute this k matrix, k vector. Now, the second part, if you recall, that we want to show that for any initial state, the zero input response of the feedback system becomes identically 0 for t greater than or equal to 3. So we will compute first of all the response of this system by putting this gain k, or by substituting, or by using this equation u is equal to r minus kx into the plant. Substituting this u, we obtain directly this one. And finally, the closed loop matrix, or the state matrix, is given by this one, which is we are assigning as a bar. Okay, so this would be the closed loop state matrix, and this is the distribution matrix with respect to the reference signal. Now the zero input response, meaning to say that we substitute r is equal to 0, and if we see directly the equation of the solution of the discrete time system or the homogeneous system is given by this one, the C matrix multiplied by a bar to the power t, where t is in discrete in nature, times x of 0. Okay, where a bar matrix is the closed loop state matrix. Now for calculating this a bar to the power t, we can use different methods. So one method we had discussed during the week 1 is using the Cayley-Hamilton theorem. The second method is by computing the first of all the similarity transformation matrix. So this is what we have done here by computing, or by expressing a bar is equal to q times this matrix, because this should be equivalent to the closed loop state feedback matrix. And we know at the outset that the closed loop state feedback matrix should contain all the eigenvalues at 0, and these are repeated, and it would contain only one Jordan block. Okay, so this is only one Jordan block times q inverse. Now expressing the powers of a bar as, these matrices won't change because these are the similarity transformation matrix. So we can directly take the power of this matrix, where if you want to compute q, this you would get. Now we will start computing the powers of this matrix for t 1 starting from 0, 1, 2, 3, and we will see that once you reach to t is equal to 3 or higher, this matrix will always be a 0 matrix. This is the reason that the zero input response of the system is always 0 for t greater than or equal to 3. Okay. Now in the second part, we have introduced we want to track any step reference input. So this characteristic polynomial is of the plant, and this is the transfer function of the open loop system, right? As the property of the feedback controller design, we know that the numerator polynomial would be affected only the denominator polynomial would be affected because all the eigenvalues were shifted from 1 to 0. Okay, and this is the characteristic polynomial of the feedback loop. This is the controller we are now using, where we have introduced this P because we want to track the reference signal, and the transfer function of the feedback loop is now given by this, where because of inclusion of this P, we would get the overall transfer function with the denominator polynomial change multiplied by a variable P. Okay. Now, if the reference input is a step input with magnitude A, then at steady state, the output Y would be given by this one. G hat F at 1 times A as t tends to infinity, where t is discrete in nature. Thus, in order for Y to track any step reference input, we need this factor is equal to 1. That is, if I substitute or if I compute G hat F of 1, we will get twice of P from here. And if I substitute is equal to 1, we get P is equal to 0.5. Okay. So the state feedback gain matrix or the vector would remain same as we have computed in the part A. Now to track any reference input, we need to compute this P, and this P is supposed to be 0.5. So the resulting system can now be described as this, where this is the closed loop matrix and the B bar matrix would also change, and Y of t is given by this. Now the response excited by the reference signal is given by this. We are computing the response because we want to show that Y is equal to R for all t greater than equal to 3. Okay. So we can express the response of the closed loop system with input R by using the variation of constant formula, or by using the iterations for computing the powers of A. So since we know that a bar to the power t is equal to 0 for all t greater than equal to 3, so we can compute only for finite sample times. Okay, t1, 2, 3, and afterwards we know we would get a bar to the power 3 is equal to 0. Okay. Substituting the C in the B vectors, we finally obtain this one. Now we know that this reference signal is a step input of magnitude A. So I can replace all these reference signals, which are the shifted version, because they would remain the same, being a step input. So we have replaced by 1 minus 4 plus 4 times A. Okay, so finally we will get this A, which is nothing but is equal to R of t for all t greater than equal to 3. Okay. So in the above problem, you would notice that the exact tracking is achieved in a finite number of sampling periods. And this was possible if all the poles of the resulting systems are placed at z is equal to 0. So we, in the theory classes, we have discussed tracking a reference signal asymptotically when t tends to infinity. But here, the advantage we got by placing the eigenvalues at the origin is that we are now able to track the reference only in finite sample periods. And this procedure or this design is also called the deadbeat controller design. Okay, so we try to cover this concept by using the tutorial problem instead of going into the theory, because the design of the state feedback controller remains the same. It is just the aspect of tracking a reference signal in finite sample periods. Okay. In the problem 3, consider a system with transfer function. So here we have taken the single input, single output system where 1, 0, that it is a non-minimum phase system because 1, 0 is located onto the right hand side, and at the same time it is also an unstable system because one eigenvalue or one pole of this transfer function is also located onto the right hand side. Now the question says that is it possible to change the transfer function to this one, okay, by the state feedback. So if you recall, in the lecture slides we had said that the controllability property is invariant under the state feedback, and also all the eigenvalues are, or let's say the numerator polynomial is unaffected, okay, by the state feedback. But here you would notice readily that one of the 0 located at -2 is not available in the closed loop transfer function. Okay, so this aspect we had said that we would discuss during the next week when we discuss more about the observability. So first of all, we'll deal with this problem, that whether we can change this transfer function to this transfer function by using the state feedback. We also need to comment about the stability of the resulting system in terms of BIBO stability and asymptotic stability. Okay. The question is, this question is significant from the viewpoint of that if you recall from the stability week, we had discussed onto one important aspect, that whenever the system is asymptotic stable, then it implies that the system would also be BIBO stable. But if the system is BIBO stable, we cannot say that the system is asymptotically stable. Okay. So let's see the solution of this problem. Now if we place the eigenvalues of the state feedback system at -2, -2 and -3, then the system would have the transfer function given by this one. Right? The numerator polynomial would remain as it is. We can change the denominator polynomial by placing the eigenvalues here, where two eigenvalues are located at -2 and another eigenvalue is located at -3. Okay. Now since s plus 2 factor is common, this would cancel out, and finally we would have this transfer function. Okay. Now if you see that the system is BIBO stable, because all the poles of this transfer functions are onto the left hand side, located at -2 and -3. Okay. Now at the outset, we also know that by the state feedback, that for the obtaining the state feedback system, we have deliberately placed the eigenvalues onto the left hand side. So this system would definitely be asymptotically stable, because the closed loop system implicitly would have all these eigenvalues onto the left hand side. Okay, so since there is some cancellation, so some property or some dynamical properties of the systems are lost. And this, what are these properties, how are they lost, we would cover during the observability week. The next problem deals with the limitations of eigenvalue placement. So consider the continuous time system with A, B matrices as given as this. So the first question says that can a gain matrix K be computed such that the eigenvalues of the system can be placed at any arbitrary position. The next part we need to comment on the inference drawn from the results. So this is a very important result which we had discussed during the lecture slides. So here, if you see that we only need to show the controllability, whether the system is controllable, because if the system is controllable, then we can place the eigenvalues of the system at any arbitrary position. Now this, here we are showing numerically that what eigenvalues could be shifted or could be placed arbitrarily. Okay. So let's see the system. Once we compute the rank of the controllability matrix is 1 and not equal to 2. So we know that the system is uncontrollable, and we cannot place the eigenvalues at any arbitrary location. Now if we try to find a state feedback gain using this formula, determinant of Si minus A minus Bk, by putting it equal to 0, the characteristic equation becomes this. Okay. Now here K we have chosen as K1 and K2. Okay. Now once we substitute K here and the A matrix form here, the B matrix here, and solve this equation or open up this equation, we obtain this one. One important thing you would see that the gain k or one of the elements of the gain vector k is not available here, which is k1. Meaning to say that we can place or we can use any value of k2 to place the only one of the eigenvalues. This eigenvalue would remain as it is. That is one of the poles located at -1. It cannot be changed. But the another eigenvalue which is located at 2, meaning to say that the system is an unstable system, we can place it anywhere in the sphere. Okay. So the inference what we have drawn from solving this problem, that if the pair AB is uncontrollable, then there are limitations on eigenvalue placement for the system. It also shows that depending on the rank of the controllability matrix, that only one of the eigenvalues can be placed anywhere. And this inference you can also obtain by using the decomposition, using the uncontrollable decomposition, and then extracting the controllable part and the uncontrollable part. So the controllable part would be this one, and the uncontrollable part would be this one. And since the uncontrollable part is having the eigenvalue onto the left hand side, meaning to say that this system would at least be stabilizable. Okay. So in the problem 5, we will see the design of the state feedback gain by using two methods. One is the Lyapunov method and another is the eigenvalue method. The objective here is that we want to place, so for these matrices A and B, we want to place their the eigenvalues of the closed loop at -1, -2, -3. Okay. Here we want to see numerically that if we use two different methods for computing the state feedback gain to place the eigenvalues at the same location, whether that vector or whether that gain or those gains would be same or different. Okay, so this problem we would see with the single input variable case and also with the multi-input variable case. Okay, because the dimension of the B matrix, or it contains two number of columns. So first we will solve the single input variable case. So recall from the lecture slide 18 the method of computing the state feedback gains using the Lyapunov method. So first we form a matrix F so that the eigenvalues of the matrix F would be at the desired location. So here we are using a diagonal matrix so that the eigenvalues would readily be visible at -1, -2 and -3. So the second step, if you recall, that we choose k bar, an arbitrary k bar, such that the pair F transpose k bar transpose is controllable, and then we solve the Lyapunov equation as this one to finally compute this T matrix. Okay. Now solving this equation, you can use the Lyap command, that is to say this is a MATLAB function Lyap, to compute this matrix T. So we compute this matrix T, and we have also commented during the lecture slide that this T matrix should be non-singular. Otherwise you cannot compute the state feedback gain using this equation, which involves the inverse of the T matrix. Okay, so from there we compute k is equal to this one. Now if we use the MATLAB place command, which is equivalent to using the eigenvalue assignment method, then we also computed the same gain vector. Okay, so either we use the Lyapunov method or we use the eigenvalue assignment method. For the single input variable case, we obtain the same feedback gain vector. Okay, so now we would verify that whether this equivalence also holds for the multi-input variable case. So these are the AB matrices given to us. We need to place the eigenvalues. So we form the F matrix containing all the eigenvalues at -1, -2 and -3. Okay, so first of all, again the first step, we choose k bar, an arbitrary k bar, such that F transpose and k bar transpose is controllable. Okay, now using this Lyapunov equation, we solve for t. Now, if you recall that in the multi-input variable case, we cannot ensure the non-singularity of the t matrix always. But here, fortunately, we have chosen this k bar in such a way that the t matrix becomes non-singular. Okay, so now using the equation, that is k is equal to k bar t inverse, we compute this state feedback matrix and we put a subscript as Lyapunov so that we can identify that this matrix has been computed by using the Lyapunov equation method. Okay. Now in the MATLAB, we can use this place command to compute another state feedback matrix which is given by this one. Right. Now if you see this equation and this state feedback gain, they both are different. That both the design K matrices, they both are different. Now it could be verified that if we use either of the state feedback gain matrix, the eigenvalues would definitely be placed at the same location, -1, -2 and -3. So let's see the response of the system by putting this two different state feedback in. So one we have the K-Lyap and another we have the K plus. So you would see that we obtain the same state trajectories when we apply these two different state feedback gain. So for the Lyapunov case, we have the less control energy. If you want to compute the control energy, you can compute by using the formulas introduced in the earlier weeks. But by using the place command, we are getting higher energy, or the as it appears at least in the signal U2. Okay. While here the U1 trajectory is more subtle than the U1 trajectory for the first feedback loop. Now the last problem deals with the state feedback and tracking. So this is a more practical example where we have considered an aircraft which is in fact during the landing phase, where the aircraft, okay, let's recall this system description. So this is the ground. Now there is some glide slope where we want to land this aircraft along this trajectory, and afterwards it will go onto the runway. Right now, in practical setups, we generally have the instrument landing system, what we also call the ILS, on the ground, which basically determines the difference between the actual trajectory of the aircraft and also the reference trajectory imposed for the descent. Now the reference trajectory is basically this one given by the glide slope. Okay, that the error whatever the height of the aircraft is from the center of mass, and it should descend along this glide slope to finally run onto the runway to lower its speed. Now in this system description, we have not taken the lateral and the rolling movements of the aircraft, but we are only concerned with the longitudinal motion, assuming that the lateral movement and the rolling movements are being handled by another automated system. So three outputs that we are measured in real time is the speed v. So the speed v of the aircraft along this glide slope, the angle of attack gamma of the flight path from the horizontal axis. So this one is the angle of attack, and the distance from the center of mass of the aircraft relative to the glide slope. So this H error. Okay. Now the control inputs of the system are the aircraft thrust applied into the aircraft axis, which is defined by this variable t, and the elevator command delta. So if you have some information about the aircraft, so these elevators are basically located at the backside or onto the wings, or which we also say the empennage. Okay, that basically controls the pitch of the aircraft. Now here we have assumed that there are no dynamics between the elevator command and the angle of attack alpha. This angle of attack is basically the angle between the aircraft axis and the axis along the glide slope. Basically this one, angle of attack, alpha of the wing. Thus we view alpha as equivalent to delta, and consequently, for the sake of simplicity, we treat alpha as the control input instead of the elevator command delta. Okay, so the thrust controls the speed of the aircraft. So if you want to get to know more about the system description of this aircraft during the landing phase, I would suggest you to go through this reference, which is given in the footnote. Now, the nonlinear model of only the longitudinal dynamics of a jet aircraft is basically given by this, where we have the differential equations in terms of the velocities, the gamma, which is the flight path, angle of the flight path, and also the distance between the center of mass of the aircraft and the glide slope. And the objective is that the aircraft follows along the glide slope, making a desired flight path angle at 3 degrees in the clockwise direction. Okay, so since we are taking the anti-clockwise directions as positive, so for the clockwise we would have minus 3 degree. Thus, it would make h error equal to 0. Okay. Now here we are using the linearized model to design the controller, where the trim conditions are taken at alpha is equal to 2.686 degrees, and the thrust has been taken as 4.23 into 10 to the power 4. So by using the MATLAB commands, you can compute the trim points of the nonlinear model, and around those trim points you can compute the linear state space equation, basically the AB matrices for these trim points. Okay, so this is the nominal state space equation. The second one we are using, we are expressing z is equal to c times x, where c is taken as identity, so meaning to say z would be equal to x. We have taken y is equal to c naught x because we only have the we want to control only two of the outputs. If we see c naught is then among the x, which is taken as the velocity, the angle of the flight path, and the h error, we only want to track the velocity and the h error. Okay, by using the control inputs, the angle of attack and the thrust. So now the control problem becomes that we want to design a controller such that the state of the closed loop system is stable. This is the first objective, and tracks the output signal given by this. Okay, so we have two objectives, the stability of the closed loop system, and another we want to track it. So one of the method we had discussed during the lecture slide is by either using the feed forward gain. So we have expressed the control signal as u is equal to PR minus k times x. Okay, so in this problem we would use another method of designing the state feedback controller, which is stable and tracks the output signal. Okay, so if you recall, let's write it. So first is the stability of the closed loop. Second is the tracking, R of t. Okay, so for the stability, we can design a state feedback system by using, let's say, us as minus of k times x. Okay, now for tracking, here we would design a multivariable PI controller, because if you recall from your UG control class that for tracking a reference signal, PI controller gives a better performance. So let's say we say ut as a multivariable PI controller in terms of kp error plus uh, ki integral of et. Okay, so if I combine both these input as the actual input, that is us plus ut, I would have minus k times x plus kp e of t plus k2 integral e of t dt. Okay, where my error signal is r minus y of t. Okay, r is the reference trajectory and y is the output of the system. Now here we will show that we can achieve both the objective by using the method we have introduced during the lecture slide. So I will parameterize all this system as a designing of the state feedback gain. So this is ki. So let's see, I can express my u also as minus k, kp and ki, where my this vector would be x e of t in the integral of e of t dt. Okay, which again can be expressed as some k tilde and x tilde. Okay, so my overall controller is now given as where my output of the controller remain the same as u, which is equivalent to k tilde and x tilde, and it is nothing but the state feedback. So here we would see that by using the principle of the designing a controller using state feedback, I can in fact design a PI controller which is multivariable in nature. Okay, so if we see the closed loop system, this is how it would look like. That these are the aircraft dynamics, the nonlinear system around some trim conditions, which is the actuator. So delta and thrust would be two output of the two input to the system. Here is just the trimming block which we use in the simulate, and these are three states: velocity, gamma and hr. Okay, and here we can place this entire controller as it is, where if you see that we require information of two things. One is the state, the original state of the plant, and also the error signal which is given by r minus y. Okay, so here we compute this error signal. This is the error signal r minus y, where this r are the reference trajectories r1 r2, and here we are taking the y by taking only the first output and the third output. Okay, so from here we compute this error signal, and this input to the controller is z, which is nothing but equal to x. Okay, because C is the identity matrix. Now since this is a state feedback, and if we see that our original plant is given by this one, and we need the state as x tilde instead of x to finally design this k tilde matrix. Okay, so we will parameterize our plant into this new state variable which we are defining as x tilde. Okay, so let's see. So let's write a couple of equations. So we would have the first x dot is equal to ax plus bu. E we have defined as r minus y. So if I take the derivative of this error, I would get r dot minus y dot. Okay, since r is a constant signal, the derivative of r would become equal to 0, and we would have minus y dot, and y is nothing, is equal to cx. So we have y is equal to co times x. So I can write as minus co x dot. Okay, so I would get e dot is equal to minus co or c naught x dot. Right? So let's write the state vector as x tilde x e and integral of e. Okay. So for writing a parameterized state equation, I would take the derivative of this x tilde, which would be x dot, e dot, and e. Okay. I need to form this matrix where we have this x tilde as x, e, and integral of e plus some matrix into u. We don't have the reference signal r, or possibly we could write and see whether we get any distribution matrix for the reference signal. So if I use this equation, first equation, to form this state matrix, I would get A. I don't have any relationship between E and E0, so these components would become 0. The B matrix would come, and simply we don't have any relationship with R into the first equation. The second equation, E dot, I can express as as the derivative of x dot, which is again I can write as minus c naught ax plus c naught bu. Okay, by putting x dot from here to here. So if I write the equation of E dot, we would get minus c naught a, and we don't have any relationship with E and integral of E. With respect to u, excuse me, this would be a negative sign. So here we would have minus c naught b, and again okay. Now here if we see E, we already have E here in the state, so I can write as this one. Okay, so we don't have any distribution matrix with respect to R. So I can write this new state space system as x tilde dot is equal to a tilde, where I have this a tilde, x tilde plus new b tilde and u. Okay, now using this equation, using this new state space equation, I have the access to x tilde, and I can design my state feedback matrix as this one. Okay, the dimension of this x would depend on x e. So if we have x as 3-dimensional, e is 2, again integral of e is 2, so in total we would have 7-dimensional or 7 dimension of or 7 variables of this x tilde. Okay, so this is how we can compute this k tilde, and once we compute this k tilde, I can extract this k, kp and ki from this k tilde. Now implementing those controller into the feedback loop, we can see that how the response of the system comes. So this is the overall response of the closed loop system. If I synthesize the k matrix with that parameterized system, this is the input, this is one of the states, so gamma should stay at -3. So it is clearly visible that this gamma is tracking the -3. The velocity should track the value 81.8, which it is also tracking, and h error should be equal to 0. So all the state variables or all the outputs are tracking the reference trajectories, and all the signals are stable. So using the principle of the state feedback design, we have in fact designed the PI controller which tracks and also stabilizes the system at the same time.